In this video, I will go through the first phase of the control theory way of working, which is called the system analysis. The purpose of this phase is twofold. First, we have to get to know how the system under examination work, and second, we have to understand what our control strategy shall secure at the end of the day. Control theory helps us with both, and today I will show you how to use the four horsemen for analyzing systems and how to creatively use mathematics for formulating control goals. Finally, at the end of this video, I will leave you with a simple exercise so you can practice a little bit, and if you want, feel free to write your solution in the comment section below so I can give you some feedback. Hello guys, and welcome to Control Theory in Practice. The development of complex decision-making policies, also known as control strategy, is typically a multidisciplinary task that involves different stakeholders with different background, and they can include medical doctors, engineers, authorities, and so on. And therefore, at the very beginning, and at the very least, you should try to understand their way of thinking, their way of communicating, and also their vocabulary. This is central here because, depending on the context, people may have a different way of thinking, they may value some aspect over others, and also the wordings can be different. I mean, the same word may have different meaning depending on the background of the stakeholders. This means that misunderstandings are just behind the corner, and they may be unobservable until the late stage of development, and then we are in trouble. After having aligned with these things, then we can proceed into a deeper system analysis by figuring out who are what I call four horsemen, which are the input, the output, the state and the disturbance, and we have to formulate a clear control goal. So let's take pen and paper and let's dig into it. The state is the set of quantities that describe our system behavior. For example, if you are studying the motion of a vehicle, then the system state can be described by the longitudinal and the lateral speed and by the longitudinal and lateral acceleration. So we can define a state vector x by stacking these quantities on top of each other. Obviously a vehicle is a much more complex system with many more states, but here we are studying only the vehicle motion and we have to consider only what is relevant for our goal. Next we have the input. The input is what we can somehow manipulate for changing the state. If we take again the example of the vehicle motion, we can see that the state changes as we change the propelling force, the braking force and the wheel steering angle. So we can rewrite something like this. But watch out! In reality, we cannot directly change the defined input u, but we need some external device to manipulate it. In practice, while we are driving, we change the defined input u through the steering wheel, the pedals and the gear shift. For instance, the accelerator pedal changes the air-fuel ratio in the engine that implies a change in the power on the propeller shaft. The gear shift, in combination with the clutch pedal, changes the gear ratio in the gearbox that transfers the power from the propeller shaft to the driver shaft. Next, the drive shaft generates a torque on the tire and the tire ultimately generate the propelling force. Then with the brake pedal, we activate the braking pad to generate the braking force. And finally, the steering wheel acts on some universal joint that change the wheel steering angle. But let's arrange things a little bit better. As seen, we have a situation like this. What we did is essentially to redefine our input u by including what we can actually manipulate and to connect it to some device that have some internal state z. Then the output of these devices, let's call it W, ultimately change the system state X. So we have that the input U changed the state Z, that changed the output W, that changed the actual state X. Now, the devices in the middle block are called actuators. In general, actuators are devices that change some quantity into some other quantity and that can possibly have internal state. For example, a combustion engine is an actuator that converts air and fuel into mechanical power and exhaust gas, and a braking system converts the brake pedal position into a braking torque. The interesting thing of this framework is that whatever we change in the left side of the picture will not change what is in the right side. For example, we can even replace the steering wheel with a gamepad, then the real system input W is still the same. Or, if you use an electric motor instead of a combustion engine, then again the input W still remains the same. Now, when we have to establish the boundary of our system, how shall we treat the actuators? Well, the general rule is that if the actuators are fast, then you can simplify your scheme by throwing them outside of the box, but if they are slow, then you have to keep them in. For example, if the conversion between the accelerator pedal position and the propelling force is instantaneous, which means that the whole propulsion system is extremely fast, then we can safely drop it and we can simplify our scheme. If this is not the case, then we have to keep it in the box. Anyway, assume that all the available actuators are very slow. Then we have to define a new system with an extended state vector that includes the actuator state, that could be the electric machine speed, the current gear, the brake caliper position, and so on, in addition to the original state X that included longitudinal acceleration, longitudinal speed, and so on. The state of the new system is X and Z. The next horseman is the disturbance. The disturbance is still an input that changes the state, but differently from the normal input U, we cannot manipulate it. At the most, we can measure it. In our example, a disturbance could be due to the wind or the slope of the road. Again, you cannot manipulate them, but as you can see, they change the state. Finally, the output is a function of state, input and disturbance, and you can define them as you want and as many as you want. If we want to be a little bit philosophical, then control theory defines outcomes as function of your choices, your state, and eventual disturbances. Anyway, the most typical output is represented by the sensor that measures state, disturbance, and so on. Sometimes you can measure the full state, some other times you can measure only part of it. Nevertheless, the output is not only what you can directly measure. As said at the beginning, the output is a function of state, input and disturbance, and therefore we could define other output depending on what we want to achieve. Typically you define two outputs. The first is what you can directly measure. In this case it's called the measure output and it essentially represents the available sensors. And the second is connected to what you want to achieve. In this case it's called the performance output. But now, given the dimension sensor, let me spend a few words on it. As for the actuators, sensors are devices that change one quantity into another. Again, as for the actuators, you should figure out if they are fast or slow and then you decide if embed them in the system or not, exactly in the same way we have done for the actuators. But let's go back to our main scheme. Now, assume that we have everything bad, I mean both the sensor and actuators are slow, then the new system state shall include the vehicle motion state, the actuator state, and the sensor state. In this case, the measured output of the overall system could be some voltage, current, and so on, depending on the type of sensor that you are using. Now, to be very precise, I define the input and the disturbance as quantity that change the state and the output as a function of input, state, and disturbance. Nevertheless, I emphasize that the input and the disturbance typically change the state. In reality, they could directly change the output without passing through the state. For example, if you consider sensor noise, you can consider it as an external disturbance that changes the output but not the state. In the vehicle motion example, this means that such a disturbance changes the measured longitudinal speed, which is an output, but not the actual, which is a state. We can summarize the four horsemen with this scheme that you can see as a placeholder that you can use in every application domain. In our vehicle motion example, we can fill this placeholder with the quantities that we identified so far. So at the end, we have this situation. Note that this time I assume that both the sensor and actuators are very fast and therefore I'm considering only the state X that describes the vehicle motion. Further notice that the measured and the performance output are not necessarily disjoint. For example, the longitudinal speed can be both something that we want to control and something that we can measure, so it appears in both the measured and the performance output. Okay, now this is a nice analysis framework, but when someone calls us, it's because they want to control a system, not because they want to draw some weird plot. But what does it really mean to control in this framework? Well, to control means to manipulate the input, to achieve a certain goal given the available information. Imagine now that it is us to control the system, namely we have to take decision on how to manipulate the input. We do that based on a goal that could be, for example, to drive at a constant speed of 80 km per hour, and we adjust the system input depending on what we see, hear and feel. Our eyes, ears and body represent our sensing system, if you think a little bit about that. Okay, nice and whatever, but again, the stakeholder didn't call us for just driving a car. Imagine instead that they want to design a cruise controller. So, this means that they want to replace you with a computer and they want the computer to manipulate some of the input. Now, given that the cruise control is used for regulating the longitudinal speed and given that the longitudinal speed changes with the accelerator pedal and with the gear, then the onboard computer shall only regulate some elements of the input vector u, while leaving some other elements to the driver. Now we assume that the stakeholders don't want the computer to touch the braking pedal and the steering wheel, so the driver manipulates them. So now we are in a situation that there are two inputs that we cannot manipulate any longer, but still they change the state of the system, and therefore they become disturbances. Do you remember the definition of disturbance? Finally, the scheme is complete with R, which is a desired speed that the driver can set, for example, from the cluster or from the steering wheel. Next, we have to figure out the possible range of the 4 horsemen. And after that, we can formalize our goal in a control theoretical fashion. Imagine that the ranges of the 4 horsemen are this. When I talk about range, I mean the possible values that each element of each horseman can reach. Note that I added a unit to each element of each horseman. This because what you want to do at the end of the day is to control quantities. The mindset shift to perform here as a control theory guy is that you don't want to control a vehicle, which is what you may hear naively from some stakeholder, but you want to control its longitudinal speed. A vehicle is not a quantity, its longitudinal speed is. Anyway, if you cannot really attach units to the 4 horsemen, be sure that what you define can be at least converted into some number. Know that finding the possible range of the 4 horsemen can be a very tedious job, but the good news is that very often you don't need to specify them for each single element of each single horseman, but it is mandatory that you do it at least for your manipulating variables. Nevertheless, the hurdles are not over. That is, when you talk with the stakeholder to find the possible range, they provide you with only the desired range. Let's clarify. What the stakeholders want is typically a subset of what can possibly happen. This means that they tend to give you specification like this. And that's all. But in reality, to design a good decision-making strategy, we should also know what can happen, which is a larger set of possibilities. For example, if you look at the longitudinal speed and the lateral acceleration, it is not difficult to see that the desired range is contained into the possibility range. If we want to be a bit more elegant and general, we can rewrite this thing about the possible versus the desired in a compact mathematical form. This reads that our state, input and disturbance shall belong to a target set which is contained in a possibility set. For example, a requirement for our control system could be that the desired longitudinal speed should be between 70 and 90 km per hour, which is a subset of speed contained in a larger set 0 to 120, which is in turn the set of the possible values that we could get. The same applies for the input. For example, for some reason, the stakeholder wants the cruise control to move the accelerator pedal position only in the range 10-90%, but we all know that the possible range for the pedal position is 0-100%. For the disturbance, it does not make so much sense to talk about desired value, because the disturbance is something that we cannot control. But still, the stakeholder often provide you with desired range for state and input, and then they mean that those ranges should hold only for a small range of possible disturbance. So we have to interpret the target disturbance in this way. In general, if we think a little bit philosophically about this concept, we can see that the set of the desired outcomes is typically contained in the set of the possible outcomes. Now the thing is that in control theory you have to figure out both. Finally, the output, being a function of the state, input and disturbance, has its range derived from the stream. Nevertheless, it may happen that you get certain output range, and from that you should identify the ranges of some missing horsemen. Note that a subset could be even just a point, like for example we want that the cruise control lead to a longitudinal speed of exactly 80 km per hour. In this case we have a subset which is just a single point, and there is absolutely no problem with that. Now, although the requirements seem very well posed now, in reality this is not enough yet. This is only the first step for defining the so-called steady state and transient specification that are the common name that we use in control theory. Now, with the four horsemen at hand, and including their possibility set, let's further refine the target set to sharpen our control goal. In the cruise control, we want the longitudinal speed of the vehicle to converge to some target speed r, which is set by the driver, and to stay there no matter of the road grade, the wind speed, and so on. Then we can define a performance output, which is the longitudinal speed, and we can write something like this. This reads that the output y should converge and stay on r for all the disturbances from d1 to d4. Anyway, note that we excluded the brake pedal position because, as said before, the stakeholders don't want us to touch it. And this is just an example of writing a control goal, but we can still exploit a mathematical formalism for writing other goals. For example, imagine that the stakeholders are willing to accept some tolerance around the actual target speed. Then we can write something like this. This means that we are allowed to be 5 km per hour above or below the target speed. For example, if the driver set r equal to 80, then the desired set becomes 75-85 km per hour. Now, by looking at the four horsemen, lot of natural and legit questions naturally pop up, and we can really sharpen our requirements. For example, what about acceleration when driving in cruise control? Can the cruise control accelerate arbitrarily fast, or there is any limitation on it? Then the stakeholders may tell you, oh, that's a good question. No, we want the cruise control to be smooth. Never accelerate too much when in cruise control. Fine, we found another requirement that nobody was thinking about. Or you can ask if there is any limitation on the lateral acceleration because of some comfort thing that they may have forgot to tell you. If we include these new requirements, then we can rewrite our performance output and express a specification like this. On the goal on Y3, we added an absolute value to say that we don't want an acceleration higher than 1 meter over squared second, both from the left and the right side of the vehicle. Note that on Y1 we didn't put any absolute value. This means that we have an upper limit but we don't have a lower limit, which means that we have a limit to accelerate but not to decelerate. Note how we are using mathematics in a creative way for expressing goals, and we are not doing anything weird with the theorems, lemmas or propositions. We are just using mathematics merely as a descriptive language to express requirements. Nothing more and nothing less than that. Anyway, the requirements seen so far are called steady state specification in control theory. This means that if for some reason we go outside of this subset, for example, if the lateral acceleration at some point exceeds 1 meter over squared second, or if the longitudinal speed drops below 80 km per hour, then the cruise control shall automatically adjust the input in such a way that the actual output reconverges to this target set. Nevertheless, if we go out from this target set from some reason, it's not difficult to imagine that there are many ways to reconverge into it. Now, the desired way of converging into the target set when we are out is encoded in the so-called transient specifications. Let's take this scheme again. If the driver changed the target speed from 80 to 90 km per hour, then he is essentially changing the target set. Now, if the actual speed was 80 km per hour, we are out and we need to converge to 90 km per hour. At this point, the cruise control shall change the available input, which include the accelerator pedal, and it must eventually change gear, to converge into the new target set. Then we have a certain vehicle speed behavior while reaching the new target set. From this transient, we can identify some quantities like rise time, overshoot, settling time, and so on that are very popular in control theory. Then we can put a requirement of them, if needed. The cool thing here is that you can provide this specification from any input or disturbance to any output. We could, for example, write transient specification from the wind speed to the vehicle speed. This means that for a sudden change in the wind speed, then the vehicle speed shall decrease at most of a certain value, and when it goes back to the target speed, then we allow a maximum settling time, and things like that. Again, you can use the standard concept as rising time, overshoot, and settling time for specifying transient specification, and you can do that from any input or disturbance to every output. In conclusion, we can fit any system in this 4 horsemen framework. Then, after we analyzed our system in terms of available sensors, actuators, fast and slow dynamics, and so on and so forth, we can put a box around it and we can call it plant, process, or system, which are the typical control theory words for indicating it. Then we embed this block into a standard and always valid control scheme, no matter which field you are working on. You change area, then you change plant. For example, you could do something like this if you are studying the problem of the economic growth of a society, or something like this if you are studying the way of improving the treatment of some disease. But if you think a little bit higher, you could even replace the plant with something like this. At the end you set goals, you sense information and take decisions every day, and there is always some disturbance that try to prevent you to reach your goal. As an exercise, if you want, try to think a little bit how to map what you are doing right now in your life into everything that we have seen today, including the desired and the possibility set, and also try to define your transient and steady state specifications. This was the last part of system analysis. To make a recap, here we have seen who are the 4 horsemen, which represent the first step toward the so-called state space representation that we will see in another video, and how we can specify control goals in terms of steady state and transient specification simply by combining the 4 horsemen. Note that this approach is valid for every application domain. I hope that it is clear what the system analysis is all about. Perhaps someone has noticed that all the focus was devoted on the what. We never touched the problem on how to design a control system. That will come in some other video. Anyway, I can tell you that if you do properly this stage, then the design of the overall control system will be much easier. In my experience, this is often the most tricky part because you have to deal with a lot of people with different background and they often don't understand your points, and this happens because this control theory thinking is not very well spread. When you ask questions around time constants, possibility set, and so on and so forth, people may not understand you, but at the same time they can understand one each other, so you can easily become the dissonant voice of the team. I am pretty sure that many of you that are watching have been there. Nevertheless, I'm going to share 3 tricks that come from my little experience and that may help you in overcoming these hurdles. But watch out, I'm not telling you that they will always work, but sometimes. The first is stay humble. Try to avoid pushing your solution only because you are the control expert and blah blah blah. Instead, try to keep a low profile, especially if you are working in an application domain that you never worked before. Listen, carefully observe, but try to avoid to stay in the corner. Instead, make the other team members to feel your presence and your interest in that subject. This means don't be afraid of asking questions, even if they are trivial. We all have been beginner in something, and someone in the team knows it. Also keep in mind that there is always someone in the team who really deeply believes in that project, and they have all the interest that you are up and running as soon as possible so that they can leverage on your skills. Second trick. Once you understand the context, the goals, and the 4 horsemen, by the way, a small parenthesis for the control theory purists that are watching right now. I call them the 4 horsemen because I could not come up with a better name. I could talk about the state space representation, but we don't have an underlying model yet. So if you come up with a good suggestion, drop a line in the comment section below. Anyway, I was saying that once you clarify the context, the goal and the four horsemen, try to secure some time for developing and testing your own solution. But why I'm saying that? Well, because you may end up in a situation where you are requested to implement some control strategy that you really don't believe that will work fine. So you can agree that you will implement it anyway, but you also want the chance of developing an alternative solution, and then you will compare both and you take the best out of them. Third trick. Try to keep the mathematical formulation only for yourself. If you show mathematics to the rest of the team, there is a high risk that they will feel like that they are dealing with some newly graduated students, nerdish theoretical guy, while they are struggling with the real world problem, they are delayed, they have a lot of problems, and they will perceive you like that you are wasting their time. But if you convert the mathematical language into the natural language, then you will have exactly the opposite effect. People will be like, oh, I haven't thought about that. Wow, this guy is very smart, he always has good points. And it is also funny when you translate the mathematical language into the natural language that you can find often very basic questions that put experts in crisis. I have a story for that. While I was doing a previous video, that you can find it here, I wanted to include the example of the photosynthesis of the plants, but I had a little concern. When a plant is doing photosynthesis, it is essentially producing its own food, which is a state, and I was wondering if there is an upper limit to it. I mean, when a plant is full, does it continue to do photosynthesis or does it stop at some point? I asked this question to a friend of mine who holds a PhD in biology, and she extensively worked with plants. And she was like, oh, that's a good question, I never thought about that. And then she got very curious and she started to Google around on the spot, and she could not find any answer to this question. Next, I want to share something that I've recently discovered. I read somewhere that there is an actual difference between goals and objectives. For instance, a goal is a long-term target, whereas objectives are sharper steps that you need to perform in order to reach your goal. So to me, when you set objectives, you somehow already made a decision. In other words, you set your input U. This is why in this video I always refer to control goals. Moreover, goal and objective seems to have a fractal behavior. I mean, how do you distinguish them if I do something like this? I mean, you can always expand up and down. If someone has clearer ideas, please drop a line in the comment below because I'm very curious. Finally, as promised, I'm going to leave you with a very simple exercise. Consider this room and assume that on the ceiling there is a fan that you can control. In this room you have doors, windows, outside can be rainy, sunny, and there are people that can step in and out. And your goal is to keep this room temperature between 18 and 20 degrees all the time. Can you identify the four horsemen and formalize the control objective? Please write your answer in the comment section below. This was all for today. In my next video I plan to give you more examples on system analysis. In the meantime, thank you for watching, and if you haven't done, please consider to subscribe to the channel, and see you next time.